Hi class. In this part of Chapter 15, we're still in the Part 2, the second part, but we've been talking about the HR diagram and main sequence stars. Stars that are burning hydrogen into helium, living their normal life, and we saw a lot of different properties of these stars. We saw that luminosities vary quite a bit, temperatures vary quite a bit, and we go from the stars that are cool and red on the lower right part of the HR diagram to stars that are big, bright, and blue and hot in the upper left part of the HR diagram. And that line, that diagonal line from the lower right to the upper left, is our main sequence. And those are stars that are living their normal lives, burning hydrogen in their core. So what happens then after those stars start to die, as they start to run out of hydrogen in their core? We'll look at the process in more detail later on, but for now we're just going to talk about the properties of these things that become of the main sequence stars, and those are giant stars, supergiant stars, and ultimately white dwarfs and other things as well, possibly neutron stars and black holes that we'll get into later. So here's a little picture, kind of a scale diagram of a couple different stars. Our sun is this tiny little dot right here, and we know how big our sun is. Our sun has, you could fit, a little over 100 Earths across our sun. So there's our tiny little sun right there. And here is a giant star. And that's a pretty big star. It's a giant star. But here's Betelgeuse, which is a supergiant star. So just look at the incredible size differences between these different stars. These giant stars can be just enormous. Our sun won't get to be quite this big, but it'll grow. It'll get bigger as it ages, and we'll talk more about that later. So as the stars die, as they live their lives, we saw that mass is a big factor. The bigger the mass, the brighter the star, the bigger the star, and the shorter its lifetime. The faster it uses its fuel, the hotter it is in the core, and the fusion reactions go much faster. So it doesn't live as long. The star doesn't live as long. And as the star dies then, as it runs out of hydrogen in its core, the core starts to contract from gravity because of gravity squishing it, and the temperature increases on the inside. That increased temperature causes an increased rate of fusion that pushes outward against the outer layers of the star, and the star gets bigger on the outside. And so as the star gets bigger on the outside, it gets larger, but the outside areas, the outside surface cools, and so it starts to look actually maybe a little more red than what it looked before. So what you get is you get a giant star that often looks a little bit redder before. So you might call that a red giant star. And if conditions are right, if there's enough mass and if the temperatures get hot enough on the inside, you can get a supergiant star. It just gets even bigger. And so the bigger the outer layers get, when you think about a gas, as a gas expands, it actually cools off. So these big giant stars can be very red stars. They look very cool on the outside, but it's kind of deceiving because they're actually very hot on the inside. And then these big giant stars eventually die, and it doesn't take too long for them to die. They don't live very long in their main sequence, on the main sequence, and they live even shorter amounts of time in this sort of dying phase as a giant or a supergiant. And ultimately, most of them become white dwarfs. Some will become neutron stars, and some will become black holes, as we'll talk about later on. But most of them become white dwarfs. The white dwarfs are then kind of like the glowing ember of a star, what's left over after all the nuclear fusion has been exhausted, and the outer layers of the star have been kind of puffed away. So here's an HR diagram. Just think about some of these features on here. So we've got A, B, C, and D, 4 different stars labeled, 4 different regions on the HR diagram labeled here. And we want to know which star is most like our sun. So our sun is a main sequence star, so it wouldn't be D. D looks like a giant star. And it has a temperature around 6,000 Kelvin on the surface. So it would probably be letter B, right? It'd probably be letter B. So this would be a star. Our sun would be somewhere in here, letter B. Which of these stars, same diagram, which of these stars will have changed the least 10 billion years from now? So again, think about lifetime and the fact that the bigger the mass, the shorter the lifetime. And so if you look down on the main sequence, star A might only live to be about 1 million to 10 million years old before it leaves the main sequence and becomes a giant star or a supergiant star. As you go down the main sequence here, this lifetime here is about 100 million years old. So we're talking 10 billion years. What stars are going to be changing the least in 10 billion years? So we go down the main sequence and find a star that would still be on the main sequence in 10 billion years. That would be a star that hasn't changed much. So as long as the star is on the main sequence, it doesn't change much over the course of its lifetime. It changes a little bit, but not that much. So we'd have to go down along the main sequence to find a star that lives longer than 10 billion years on the main sequence. Our sun lives at just about 10 billion years. So it would probably be one of these stars down here that lives much longer than 10 billion years. So star C, for example, would not look very much different after 10 billion years. In fact, if we are correct in our sort of measurements of the age of the universe being around 14 billion years old, every single red dwarf star way down here in the lower right part of the HR diagram that has a lifetime of about 100 billion years or so or more, every single one of those stars that has ever been formed is still alive, still burning hydrogen in its core. None of those stars have died yet. There just hasn't been enough time. So star C is our answer for that. Which of these stars can be no more than 10 million years old? Which of these stars can be no more than 10 million years old? So which star will die after 10 million years, in other words? They can't live any longer than 10 million years. Well, that would be up in the upper left part of the HR diagram. Again, these are bigger, more massive stars. And it seems kind of counterintuitive, but the more mass you have, yeah, the more fuel you have, that's true. But gravity squeezes you so tight in the core that the temperature gets so high that the fusion reactions happen so fast that you run out of that fuel way too quickly. It's sort of like if you're running a marathon and you decide to sprint the first mile, you're just going to run out of energy. You're not going to be able to complete the marathon. So you have to pace yourself. So these big, massive stars don't know how to pace themselves. They just run out of their fuel very quickly. They don't use all the hydrogen available to them. And we'll talk about some of the reasons why. There's still a lot of hydrogen left inside these big, massive stars when they die. What's in the core, though, gets used up very quickly. And that's when the star dies, when that hydrogen gets used up. So star A is our answer there. So some other things we can look at, another property of stars that we'll be interested in is stars that change brightness over time. And sometimes they change brightness in a very periodic way, in a very regular way. So these are called variable stars. So any star that changes slightly, significantly in brightness, slightly, it depends. There's some that change a lot, some that change slightly. But any star that changes on a regular basis is called a variable star. Some of these stars change in brightness because they are kind of having a hard time achieving a balance. Right, so we talked about this solar thermostat in Chapter 14. We talked a little bit about how the sun maintains equilibrium. If the core temperature were to, for example, cool a little bit, then gravity would squeeze the core a little bit, and that would cause the temperature to increase, which would then cause the fusion reactions to increase, which would then make the core actually expand a little bit, and then go back to its sort of normal size. So there's this mechanism. Because of the properties of gases and the fact that gravity is trying to squeeze the star, but at the same time the energy coming out of the core is trying to make the star expand. There's usually a nice balance there. For various reasons, there are situations where a star has a hard time maintaining that balance. So it actually gets brighter, and then it gets dimmer, and then it gets brighter, and then it gets dimmer, as it kind of alternately expands and contracts and expands and contracts. Every star might do this to some degree, but there are some stars that do this to such an extent that it's easy to see. That it's easy to see these variations in brightness. And more so you can see the brightness than you can see the size changes, but you can definitely see the brightness changes in many of these stars. And some variable stars can have periods, we call them, the amount of time it takes for them to change their brightness to get bright and then dim and then bright again. That's the period. Some stars can do this over the course of a few hours. Other stars take several years to go through one cycle of brightnesses. So there's a large variety of possibilities. So when you look at a star and you measure its brightness, you can get a graph such as this. So this would be the apparent brightness. You're just simply looking at the star in the sky through a telescope, maybe. How bright does it appear to be? And you see that as time goes on, the brightness goes down, and then it goes up, and then it goes down, and then it goes up. And you see a very regular pattern occurring. In some stars, it might not look this nice. In some stars, the pattern might not look as regular, but So there's a variety of possibilities, but often you'll see a nice pattern, and this is the period, the time over which the pattern repeats itself. And so in this case, it looks to be about 50 days. Every 50 days, the star goes from being as bright as it will be to being dim, and then being back to as bright as it will be again. So it has a 50-day period. So this is called a light curve, the light curve of the star. If we look on the HR diagram, if we look at some of these variable stars and plot them on the HR diagram, we find that many of them fall in this strip, in this particular region of the HR diagram. We call it the instability strip. The instability strip because stars in here, for some reason, are not able to maintain a nice perfect balance, a nice perfect gravitational and pressure balance. And so they fluctuate, they sort of oscillate, they vibrate in a sense in terms of their size and their brightness. Polaris, actually, our North Star, is actually a variable star. So it lies on the HR diagram along somewhere in that instability strip. There are some stars up in this upper part of the instability strip that are called Cepheid variable stars. And they're very special. What we found is by measuring the period, we have found that there is a connection, there's a very precise relationship, it seems, between the period of their brightness variation and the energy that they output, their luminosity. So why that is useful is that, remember we talked about how do we measure distances? Well, we can measure distances using the parallax method, as we talked about earlier. But that parallax method only allows us to measure distances to a certain distance, and we can't go much farther. And the whole point of measuring distance is to then take the apparent brightness of the star, combine it with the distance measurement to calculate the true brightness of the star. But if we have these Cepheid variables, and by seeing some of them and knowing their distances already, we realize that there is this relationship between true brightness, luminosity in other words, and the variability, the period. And so we see some Cepheids, we know their distances through some other methods, and we come to realize that this relationship is true. Well, now as we look around the sky, we might find other Cepheids that are just like these Cepheids, that have these periods of just a few days, and we realize that, oh yeah, this is a Cepheid variable. It's a variable star. Let's measure its period. If we can measure its period, we automatically can know its luminosity without knowing its distance. But then what we can do is we can compare its luminosity with its apparent brightness and actually calculate the distance. So this gives us another way of measuring distances to things that are much further away than what we can measure with the parallax method. And there are other methods as well. So astronomers have several methods for measuring distance, and most of them have limitations. But as you use them kind of together and you measure stars using several methods of measuring distance, you're able to kind of really refine your measurements and get more and more, better and better, more and more precise, better and better values for your distances and luminosities and everything else you're trying to measure. So in this second part, this big second part of Chapter 15 that we've been going over, we introduced the Hertzsprung-Russell diagram. So again, this is a plot of luminosity as a function of temperature. Temperature on the horizontal, luminosity on the vertical. But temperature is also related to color and also the spectral type, this OBG, etc. spectral type. So they're all kind of related to each other. And then we talked about the main sequence stars, which are your normal stars burning hydrogen in their core, living their normal life. And the more massive the star is, the shorter its lifetime, and the bigger and brighter the star is, the hotter the star is as well. So mass really tells you everything about the star. And then when the stars die, they become giant stars or supergiant stars, depending on the amount of mass available. As they run out of hydrogen in the core, then we'll talk about, eventually in a couple chapters, we'll talk about what happens then once they run out of hydrogen. What do? Do they just stop? No, they actually start converting that helium that they made into other stuff. And so we'll talk about that. And ultimately then many of these things, these giants and supergiants, end up as white dwarfs. But some will end up as neutron stars and black holes as well. We'll talk about those. And then finally we talked about the variable stars, which are stars that are sort of unable to achieve a balance, and they just kind of go back and forth, can't quite decide what they want to do. Do they want to get bright? Do they want to get dim? They can't really tell. They have a sort of a problem they have an instability problem. So that pretty much wraps up this part of Chapter 15. And the next thing we'll talk about is looking at clusters of stars, and what can we learn from looking at clusters of stars that have all been kind of born at the same time. They've all been formed out of the same big cloud of gas, but instead of one star forming, thousands of stars might have formed. We can learn a lot of information from clusters.